Good morning, everyone. Okay, so I think it's better for us to have the recording again rather than having a real time class. Last week, I did not have a class with you because I celebrated the Father's Day ahead of time, and right now, I would like you to celebrate it with family also, with your father if you're not yet married, or with your husband if you are married, or if you are the husband the more that you are going to celebrate Father's Day today. Okay, so this is in continuation of what we had last time. So I think I will be posting 2 or 3 videos that you can browse along the week. And then as much as possible, I'm going to limit my activities also. So I may not be giving activities, but then I will be giving the final requirements after I am posting 3 or 4 videos. Okay, so the thing that we're going to discuss this morning or today is about hypothesis testing. So we will start with a single sample population. So hypothesis testing coming from one population sample, and then next one is from two samples or two populations. Okay, so but then you might be asking what is a hypothesis. So for sure you have encountered the term hypothesis when you're in high school because when you do laboratory activities you need to write your hypothesis. So this is what we call a scientific guess. But in research, this is very important if you are going to test whether you're when you are going to test what you have observed in the sample, whether that is true for the population. So a hypothesis is a statement about a value of a population parameter developed for the purpose of testing. That's what I mean. Examples are this one. The mean monthly income for a systems analyst is 6,325. So the average, if we say mean monthly income, that means it's the average monthly income for a systems analyst. But it has to be tested because it's not sure yet if it is true for all. That is just an observation. Or 20% of all customers at Bovine's Chop House return for another meal within a month. So that's also another hypothesis. So when we do research, we would like to verify whether these two statements are correct. So what we will be doing is the hypothesis testing. So when we say hypothesis testing, that is based on sample evidence and it is also on the probability theory. That's why in the undergrad, before the lesson on hypothesis testing, there is a bridge between descriptive statistics and inferential statistics because this is the inferential part. The bridge is the probability theory. So there is some lessons on probability because hypothesis testing is based on sample evidence and the probability theory. And it is used to determine whether the hypothesis that you proposes or the researcher's hypothesis is reasonable statement and should not be rejected or is unreasonable and should be rejected. So there are steps in hypothesis testing. Okay, this I'm going to present to you the traditional one. Okay, so it has 5 steps. Okay, so the first step is you're going to state the null and alternative hypothesis. So sometimes it is sorry for that. It is the null hypothesis that is going to be stated because in the event that we reject the null, then the alternative hypothesis is going to be accepted. The alternative hypothesis is called the researcher's hypothesis. That is the hypothesis that the researchers would want to be accepted. The second step is you are going to select the level of significance. And in most cases, the level of significance is set at zero point zero 0.05. Sometimes it's 0.10, but zero point zero 0.01 for medical researchers, but the widely accepted level of significance is zero point zero 0.05. Then after you select the level of significance, then you identify what test statistic is that. This is the one, the tricky part. Because when you identify the test statistic, you need to understand the objective of the study. The main objective, you have to understand it so that you can identify the best test statistic. And this test statistic sometimes is parametric or non-parametric depending on the where your sample is taken. If it is taken from a normally distributed population, then it is going to be using the parametric test. But then if it is taken from a non-normal population, then it's going to follow the non-parametric test. Then step 4 is you formulate your decision rule, whether you accept or reject null hypothesis. And step 5 is you take sample or arrive at a decision. This one, yeah, reject or fail to do not reject, or this one is fail to reject. This one is reject the null or accept the alternate. Okay, so step 1. Okay, so in the step 1, when you state the null and the alternative hypothesis, the null hypothesis is the statement about a value of a population parameter, and it is usually stated as no significant difference, no significant relationship, no predictor at all. And the alternative hypothesis is a statement that is accepted if the sample data provide evidence that the null hypothesis is false. So when we do hypothesis testing, it is important that you have to, it's like trial by contradiction, because the first thing that you are going to state is the null hypothesis. Then you gather data, you provide sufficient evidence that you're going to reject the null. And in the event of rejecting the null, then your alternative hypothesis is going to be accepted. It is just like a trial in the court. So the first thing that the defendant is going to say to himself, to the court, is, "I am not guilty." So the defendant will plea not guilty. But then the katumangakihante, the one that is what you call this, the other party, they are really going to provide pieces of evidence. They will gather a lot of pieces of evidence, so that the defendant's plea of not guilty is going to be contradicted because of the pieces of evidence that is being presented. So that is the logic of the null hypothesis. That is why in the step 1, you have to state the null and the alternative hypothesis. But in the graduate school, it's no longer stated the alternative hypothesis. This is in the undergrad, in which they should understand first what is the alternative hypothesis. That's why it has to be stated. But in the graduate school, when you are going to make your thesis or your dissertation, you would not state anymore the alternative hypothesis. Okay, so there are 3 hypotheses about means. So 3 possibilities regarding hypothesis on means. Okay, so first one is the H0 there is the null hypothesis. The H1 is the alternative hypothesis. So in the statement of the null hypothesis, that means, as I told you a while ago, it is a statement of no significant difference. It is a statement of no significant relationship or no predictor. So you have to state it as always equal to 0. If it is on the means, then the average, the difference on means, or this one, if it is a one sample population, so it is the mu is equal to 0, and your alternative hypothesis is it's not equal to 0. That's the first one. The second one is when you say less than or equal to 0. So in this case of equal to 0, we say that this is the direction is non-directional. There is no direction because it's equal to 0. For this one, less than or equal to, or when you say it's less than or equal to, so that is the null hypothesis. Of course, in your alternative hypothesis, you are going to state the opposite. It's greater than, or the null is greater than or equal to 0, and then you do the opposite. The alternative hypothesis is less than. So these two, these are one directional, this one is two directional. Okay, but then sometimes it doesn't matter at all whether it's one directional or two directional. Okay, so as long as you are going to state that there is no relationship or no difference or no predictor, that is already the null hypothesis. It doesn't it doesn't matter whether it is one directional or two directional, because the difference in the slight difference on the critical value doesn't matter at all. And the null hypothesis always, oh, you have to remember that the null hypothesis always contains the equality. So there is equal to, less than or equal to, so there is still equality, and greater than or equal to, there is still the equality. Okay, so there are types of error. Okay, so the level of significance, when we say level of significance, as I've told you a while ago, is always set at 0.05. But that level of significance is the probability of rejecting the null hypothesis when it is actually true. Or the other way of saying, the level of risk in doing so, in so doing. Because there are types of error that is associated with the level of significance, as the type 1 and the type 2 error. So when we say the type 1 error, that is the probability of rejecting the null hypothesis when actually it is true. So that means if it is in the court, this is the probability nga imong you imprison a non-guilty defendant. What you call is an innocent defendant. On the other hand, on the type 2 table, okay, so in a four-way table, this is your null hypothesis, and if the researcher accepts that the null hypothesis is true, that is a correct decision. But if he's able to reject that null hypothesis, that it is true, but he rejected it and he said it is not true, then what he committed is what we call the type 1 error, or that is our alpha. So that the alpha is 0.05, that is the 0.05, so we are allowing 5% that the researcher would commit a type 1 error. And then on this one, on the HO is false. So if the null hypothesis is false, really that there is really relationship, but you accept it, although it is false, what you have committed is a type 2 error, that is the beta. But when it is false and you reject it, that is a correct decision. So these two, the type 1 and the type 2 error, are so related that if you are going to make this one stringent, let's say you are going to make this one because you don't want to make it to commit type 1 error, so you're going to set your alpha at 0.001, you are making your power of the test beta greater. So that's why it should be balanced. Sometimes the beta that is set on the online calculators, it is always set at 80%. Okay, so this table is what you call the risk table. Okay, so test statistic is the type of statistics, the statistical test that you will be using. Either you will be using a z-test, t-test, f-test, or the analysis of variance, or the chi-square. X squared is chi-square. So when you select, as I have said, when you select the test statistic, that is really based on the objective of the study. So it takes skill for a statistician. So a statistician that is just a statistician but is not a researcher, not doing any research, will find it difficult to determine what the test statistic will be used, because he is not very familiar with how problems are stated, research objectives are stated. Just like, for example, me, I used to treat educational researchers when I had my few studies done by the medical doctors. It took me a while to realize that they have a different set of stating the objectives, and they have also set up different styles of testing. They have specialized, what we call specialized sample size computation when it is a cohort study, when it is a retrospective chart review, and so on. So again, it would take skill and a lot of knowledge in choosing the right test statistic. So for the z distribution, when are you going to use the test statistic? That is when you have a large sample and the sample is taken from a normally distributed population. So when you are going to run a statistical test, the first thing that you're going to do is you check on the assumptions. It's not, I cannot discuss this one here on the assumptions, but if you're going to make your research, you may have to consult a statistician also, because you need to follow the assumptions. So you cannot use z-test if it is not coming from a normally distributed population. So there are tests that you need to run first to check whether your sample is coming from a normally distributed population. So you have to run Shapiro-Wilk or Kolmogorov-Smirnov. That is if you're using SPSS. And if you're using the Microsoft Excel, you have to look at the data analysis toolpack and you look into the skewness. And if the skewness is near zero, then you are going to say that your data is most likely normally distributed. Then on the fourth step is you formulate the decision rule. So that is based on the critical value. So the critical value is what you say the dividing point between the region where the null hypothesis is rejected and the region where it is not rejected. So for example, this one. Okay, so the critical value is 1.65 for the z, and that is equivalent to a 90% confidence level. So 1.65. And this is the probability here na if you compute, do it manually, if the value falls more than 1.65, then that is in the rejection region. Otherwise, if it is less than 1.65, it is in the acceptance region. But right now, we are not looking into the computed value and the critical value, but we're looking into the p-value. So later on, you will encounter how you're going to interpret p-value. And of course, the decision rule that you're going to create is based on that. So if it is on the rejection region, your computed value is in the rejection region, then you would say reject the null. Otherwise, if it is in the acceptance region, you would say fail to reject the null or accept the null hypothesis. Okay, so but then when you reject the null or you accept the null, there is no evidence that showed there is a difference or there is relationship. It doesn't mean that in real life there is really no relationship or there is no difference at all. It just only means that medyo kulang yung your data collection. The data that you have collected do not provide sufficient evidence to reject the null. That's how you're going to interpret it. So there must be, so if you're going to what you call this, recommend to the future researchers, you might recommend that you, in the next researchers who would like to replicate your study, they're going to increase the sample size. Otherwise, you will get the same thing of no relationship or no association or no difference at all. So that's how it is. Is the one I told you. Then the p-value, that's the one the very important one, in which we should not be doing the computed and the critical value, but you just look at the p-value. So the p-value is the probability, assuming that the null is true, of finding a value of the test statistic of at least as extreme as the computed value of the test. So the decision rule using this one, if the p-value is larger than or equal to the alpha that you set, then you would say fail to reject the null or do not reject null. But if the p-value is less than the alpha, then you would say reject the null hypothesis. So very easy, because usually in the Excel, they will just compute the p-value right away. So you have to think always that if it is greater than alpha, that is fail to reject. And if it is less than alpha, alpha at 0.05, so if it is less than 0.05, then HO is rejected. Okay, this is how you will interpret also the p-value. So some evidence like that is some evidence that HO is not true. So if it's like that, and if it is the P is between, so if the P is between 0.05 and 0.10, some evidence of HO is not true. But here, if it is real, this is on the rejection. I mean, you reject because it's greater than 0.05, but it's less than 0.10. So there is some evidence of HO that is not true. But here, if it is 0.01 to 0.05, then there is a strong evidence that HO is not really true. And if it is greater than 0.001 to 0.01, then it is a very strong evidence that HO is not really true. So here, if it is being rejected because the p-value is greater than 0.05, because you set the boundary at 0.05, so if you go beyond 0.05, then you reject the HO. It doesn't really say that there is no evidence. There are some evidence that HO is not true. But only that those some evidence that HO is not true is not enough to say and to say that HO is not really true. So you need to have more pieces of evidence to prove that HO is not really true, just like this one strong evidence and a very strong evidence. And in the step 5, of course, you have to make a decision whether accept HO or you reject HO. Then we have this one-tailed test of significance. That's the one I told you. So the alternate hypothesis states a direction, so that's the one greater than or less than, so that's one-tailed, one-directional. Just like this one, the average yearly commissions earned by full-time realtors is more than 35,000 US dollars. So that means more than, so greater than 35,000. Or the mean speed of trucks traveling in I-95 in Georgia is less than 60 miles per hour. So it is claro kaayo na, it's so clear that it's less than 60. So it's one-tailed or one-directional. It is less than. Or another example, less than 20% of the customers pay cash for their gasoline purchase. So it is less than, so it's so clear that it's less than, so it's one directional. So the sampling distribution of the statistics Z, okay, if it is a right-tailed one, that's the one that I showed you a while ago. One directional, this one lang, one shaded region. If it is two directional, it's plus minus 1.65, so plus 1.65 here. And on the other side, it is minus 1.65 if it is two-directional. Okay, so two-tailed or two-directional, that's the one. The mean amount spent by customers at Walmart in Georgetown is not equal. So the not equal to means it's either greater than or less than or equal to. So it is two-tailed, two-directional. Or you would say the average price of gallon of gasoline is not equal to $1.54, so it is not equal to, so it is two directional. This is how it looks like. This is a 95% confidence 95% confidence level, so it's minus 1.96 plus 1.96, the critical value on both sides of the normal distribution, the curve. So if it is one directional, it's either negative or it's either positive. If the direction in the hypothesis is less than, of course you will put it in here in the negative part. If it is greater than, of course it's in this part. And if it is not equal to, then both sides, negative and the positive. Okay, so test for the population mean from a large sample with population standard deviation that is known. So you have your Z test. That is this is very familiar to you, right? This is the one that I gave you as an example last time. So that is the sample mean minus the population mean over the standard error of the mean. That is the standard deviation over the square root of the sample size n. Okay, for example, the processors of fries ketchup indicate on the label that the bottle contains 16 ounces of ketchup. The standard deviation of the process is 0.5 ounces. A sample of 36 bottles from last hour's production revealed a mean weight of 16.12 ounces per bottle. At 0.05 level significance level is the process out of control. So if you're in a production, you are going to use this one. Okay, so that is, can we conclude that the mean amount per bottle is different from 16 ounces? So enough ba na evidence to claim that the mean amount of bottle is not really 16 ounces based on the sample of 36 bottles that has the mean weight of 16.12 ounces. So we will test hypothesis for this one. So this first step is state the null and the alternative. So we would say that the null is, it is equal to 16 because it is the one in the bottle, listed in the bottle. But what is found based on the sample is greater than, not, it's greater, even greater than 16, that is 16.12 if you remember. So you can either say mu is greater than 16, or you just say, because it's 16.12, or you just say to make it so simple and not complicate things, it's not equal to 16. Step 2 is select the level of significance. Of course, you're not going to do a lot of things on that because you have to always set it at 0.05. Then step 3 is you identify the test statistic, because we know that the population standard deviation, it's given the SD, the mu, and the sample, everything is given. So what we're going to use is the Z test. Okay, so here our decision rule is we reject HO if the computed Z is greater than 1.96, and if it is less than negative 1.96, or if the p-value is less than 0.05. So I would suggest that you look at the p-value instead. And if you are going to use your Excel, that can be done in the Excel, or you can just do this a manual computation, because it's given already the sample mean, which is 16.12, the population mean, which is 16, standard deviation is 0.5, and the sample size, which is 36. Okay, so step 5 is you make the decision rule and interpret the results based on your computation. So we will compute. Okay, so Z is equal to X bar minus mu all over standard deviation over the square root of n. So we are going to plug in the values given. So 16.12 minus 16 all over 0.5 over the square root of 36, which is 6. And that gives you 1.44. And if it is, the Z is greater than 1.44, and you look at the table of values again that I gave you, okay, it's 1.1499. And if you remember, Okay. So, it is less than 1.96. So, it is in the acceptance region na siya sa tunga. So, that means to say, do not reject the null hypothesis. So, we can say that based on the sample, 36 bottles, it's premature to conclude that the average contents per bottle of fries ketchup is different from 16 ounces. Okay, now is testing for population mean with a large sample, but the population SD is unknown. So if it is the SD is unknown, we estimate it with the sample standard deviation S. And as long as the sample size is greater than 30, we can still use the z-test. Only that we will substitute the sigma, substituted it by S for the standard deviation of the sample. Okay, so this example. Roder's discount store chain issues its own credit card. Lisa, the credit manager, wants to find out if the mean monthly unpaid balance is more than $400. The level of significance is set at 0.05. Random check of 172 unpaid balances revealed the sample mean of $407 and the standard deviation of 38. Okay, so should the credit manager conclude that the population mean is greater than 400, or is it reasonable to assume that the difference of $7, because it's in the sample you get 407 but the population is 400, so the difference of 7 is due to chance. So again, step 1, state the null and the alternative. So that is the null is less than or equal to 400. Okay, so this is one-tailed. Each one is greater than 400 because it's 407. But you can always go back to the two-directional not equal to or equal to like that. Dito na siya mo matter. It doesn't matter at all. Then, significance level at 0.05. Again, repeat the process. Repeat the process. So, it is... now we will do the computation. Okay, again, going back to the formula, then we have 407 minus 400 over 38 over the square root of 172, so that is 2.42. Look at it on the table. Okay, that's 0.0078 for a one-tailed test. So you say you reject HO. By the way, this value on the table, the one that we look at the table, this is now the p-value, huh? I forgot to mention that. You might be using this one, 2.42 against the 1.96 like that, but you can look at it on the table and that is using the p-value. So, when you look at the table that I gave you last time, you're not looking at the p-value. So, here, we found that it is 0.0078 and it is less than 0.05, so we reject HO. So what does it mean? The credit manager can conclude that the mean unpaid balance is really greater than 400 US dollars. Now testing for a population mean with a small sample and standard deviation unknown. So this time, if it is that case, then we will be using a t-test or a t-distribution. But I forgot to give you this table of t-distribution, but you can always download from the internet. Anything that you are not so familiar with, or I might not be able to discuss it well here, you can always consult Google. Okay, so always consult Google. So here, The critical value of t is determined by its degrees of freedom, that is n minus 1. So there was somebody last time asking for how to find degrees of freedom, that is n minus 1. And if it is a chi-square, there are degrees of freedom that is n times n minus 1, like that. So that depends also on the type of test. But for t-test, the degrees of freedom is basically n minus 1. That is the sample size minus 1. Okay, so example. The current state rate for producing 5 amperes fuses at nearly electric company is 250 per hour. A new machine has been purchased and installed that, according to the supplier, will increase the production rate. So the production hours are normally distributed. A sample of 10. So here it's only 10. Randomly selected hours from last month revealed that the mean hourly production in the new machine is 256 units. Sample standard deviation of 6 units per hour. Okay, so at 0.05, level of significance, Canary Electric Company conclude that the new machine is faster. So again, go back to those steps. Okay. And of course, you are going to look at it on the table. It is 10, so your DF is 0.0, is 9. So the T value that is on the table is 1.833. Or we will use the P value, that is, if it is less than 0.05, then we're going to reject the null. And the same formula, that's it. But this time, the computed 3.162. Again, go back to your Z. Okay, so that is 0.0058. And that is reject HO. So you can say that the average number of fuses produced per hour is more than 250 units. Now let's move on to test on proportion. So proportion is a fraction or the percentage that indicates a part of the population or the sample having a particular trait of interest. So P is the number of successes in the sample over the number sampled. Okay, so the sample proportion is P, and pi is the population proportion. Okay, so this is the test statistic. P minus pi over the square root of pi minus 1 minus pi over the square root of n. Okay, so example. In the past, 15% of the mail order solicitations for a certain charity resulted in a financial contribution. A new solicitation letter that has been drafted is sent to a sample of 200 people, and 45 responded with a contribution. At the 0.05 significance level, can it be concluded that the new letter is more effective? Okay, so the same thing, test the hypothesis, follow the steps. Okay, and this is the one that you're going to make a decision and interpret the results. So the formula P minus pi over the square root of pi minus 1 minus pi over the n. So based on the sample problem, we have 45 out of 200. Okay, 45 out of 200 people responded with a promise minus the 0.15, that is 15% of the one that promises, so it's 0.15. So 45, you get the percentage for this one minus 0.15, then all over 0.15 times 0.85 all over 200, so 2.97. Again, looking at that on the table Z. Okay, so if you look at that, it is 0.0015. So the null hypothesis is rejected. So you can say more than for 15% responding with a pledge, and the new letter that is being the new solicitation letter that is being routed is more effective than the previous one. Okay, so that's our discussion for the one sample statistics. So keep the next video is going to be on the second two sample statistics. I mean two sample test. Accepting the null hypothesis when it is actually false. So this is saying that the defendant is not guilty, but in the truth, it is guilty or he is guilty. Okay, so if you look at it on